Genique. Previously, we discussed the cylindrical, the Cartesian coordinate system, cylindrical coordinate system, and the spherical coordinate system. Here, we will discuss the differential length, differential surface, and differential volumes. Okay, how these can be calculated. And here, I will give you a small shortcut here. Okay, so that no need to use this graphical method here. Okay, because this is a crash course, I cannot teach everything. Okay, so that's why you should go for this the shortcut method here. Okay, suppose what is the differential length? The differential length is represented with dl. Okay, suppose if I want to write this differential length in the Cartesian coordinate system, okay, it is a well-known result. What is the differential length? Generally, differential length in the Cartesian coordinate system is represented as what? Suppose, how we will find the differential length? Suppose if x and y and z, okay, is transferred to b, okay, x plus dx plus comma y plus dy and z plus dz. Okay, suppose if any point A is represented x, y, z is transferred to B. Suppose if I want to move from A to B, which is having the coordinates x plus dx, y plus dy, z plus dz. Okay, so now what is the differential length? The differential length from here to here, it is this minus this into ax, this minus this into ay, this minus this into az. So that means I can write what? Dx ax plus dy ay plus dz az. Okay, this is in Cartesian. So this is the differential length in the C. This dx is the differential length in the x direction, dy is the differential length in the y direction, dz is the differential length in the z direction. So these are represented in terms of the Cartesian coordinate system. Suppose if I want to write this dl in the cylindrical coordinate system, what are the cylindrical coordinate system coordinates? Rho phi z. For rho phi z, I can write d rho a rho. I can write d phi a phi plus I can write dz az. So can I write? So if you write this like this, means it is wrong, because see, in the above expression x, y, z, these all are lengths, but here in rho phi z, what about this? This is length and this is the length, but what about this? This is an angle. Okay, so it is the length in the x direction, this is the length in the y direction, this is the length in the z direction. Similarly, what is this? It is the length in the rho direction, it is the length in the z direction. Okay, what about this? The length in the what? Phi direction. This is not the length in the phi direction. Now, suppose if you observe this, let us suppose this is the z axis. It is the z axis. Let us suppose this is having a rho. Suppose if this point is moved from here to here, okay, it is making an angle. Let us suppose this is making an angle, some d phi. Okay, this point is where rho phi z is having, this a point is transferred from here to here. Here it is having the same rho, but the coordinate is phi plus d phi and z is also z. So what is the length? What is the length in this angular direction? So the length in the angular direction can be written as, the length in this angular direction can be written as, this is represented with dl. Okay, what is this dl? dl in this direction, what is the length? This radius into the angle. Radius is what? Rho into d phi. So this dl represents the differential length in the direction of pi. The differential length in the direction of pi, in this direction. So I can write, what is this? Length, rho into d phi. So I have to write rho here, rho d phi. Okay, this is the angular distance, but if I want to convert into the linear distance, I have to multiply this angular distance with the radius of that circle. Okay, it is just like a sector. Understand? So this is d rho, a rho d phi, a phi, dz, az. Okay, suppose this is what? This is a Cartesian. This is a cylindrical. Okay, sorry. Cylindrical coordinate system. Now, if I want to write the dl in terms of the cylindrical coordinate system, this is dr, ar, and next one is theta. Theta, for theta, here also, what can I write? R d theta, a theta, here it is r sin theta, d phi, a phi. Okay, so I will give you a small shortcut here how to write this r d theta, a theta, and r sin theta, d phi, a phi. See, suppose if you take any sphere like this, okay, if we take any sphere like this, what about this? dr ar, in the r direction, this is dr ar. Okay, what about in the theta direction? What is this? Is theta, right? This is theta. This is d theta. D theta is equals to, what is the differential length in the theta direction? The differential length in the theta direction is equals to r into d theta. So that's why I have written r into d theta, a theta. Okay, what is the differential length in the phi direction? What is the differential length in the phi direction? We know. What about this? This is rho, right? Okay, already we know what is the differential length in the phi direction. Rho into d phi, right? Rho into d phi. Differential length in the phi direction, I am not writing here. Differential length in the phi direction will be, is what? Similar to this, it is rho into d phi. But what is this? If I assume a sphere, if I assume the cylinder here, then this will be the rho, this is rho into d phi. What is rho here? Rho is nothing but what? Let us suppose this is theta, okay, or rho is equals to cos sin theta is equals to what? Sin theta is equals to rho divided by r. Here rho is equals to r sin theta. So in place of rho, I can write r sin theta d phi. Simple. Okay. So like this, I can write this dl. Okay. So now, if you observe this, so wherever there is a distance term, here these all are distances. You can directly write dx, ax, dy, ay, dz, dz. Here it is a distance term. So I can write d rho, a rho, here also dz, dz. Here it is a distance term, d rho, dr, ar. But these are all the angles. So that's why I have to take the displacement in the direction of those angles. Okay. So now for this, we will give a small shortcut here. The parameters and the scaling factors. The parameters and the scaling factors. Here the parameters are u, v, w. Here the scaling factors are h1, h2, h3. Okay, so these are the parameters and the scaling factors for each and every coordinate system. So you have to remember forever. Okay, suppose if you take the Cartesian coordinate system, what are the parameters? The Cartesian coordinate system, the parameters are x, y, z. The scaling factors are 1, 1, 1. Okay. Now, what if you take the cylindrical coordinate system, rho, phi, z, here it is, because all are lengths, I am taking these all are ones. Because these two are lengths, I have to take this one and this one. So what is this? I have to write this row. Whatever this row is there, I have to write here. Okay. If I take r, theta and phi, so what I have to do? I have to take this one as 1 and remaining these two are, what is in theta? What is the scaling factor? It is r. In phi, what is the scaling factor? It is r sin theta. If you remember this, so the coordinate system is over. The differential length, differential volume and differential surface are completed if you know this. Okay. So in general, what is dl? The dl is generalized as h1 du au plus h2 dv av plus h3 dw aw. So like this, what is uvw? X, y, z, rho, phi, z, r, theta, phi. So suppose if I want to write, this is the generalized formula. Okay, this is the generalized formula. Suppose if I want to write the differential length for the Cartesian coordinate system, how can I write? H1 is 1 into dx ax, 1 into dy ay, 1 into dz az. Suppose if I want to write in terms of the cylindrical coordinate system, how can I write? Cylindrical coordinate system, how can I write? H1 is 1 into d rho a rho plus rho into d phi a phi plus 1 into dz az. Okay. Suppose if I want to write the differential length in terms of the cylindrical coordinate system, 1 into dr ar and h2 is what? R into dv. dv is d theta a theta. This one. Next, h3 is r sin theta into d phi a phi. R sin theta into d phi a phi. Simple. Okay. So you have to remember this kind of generalized formula. It is called as the generalized formula. The general expression for the differential length. Similarly, if we want to write the differential volume, differential surface area. Okay. So already we know x equals to constant surface will be having the direction ax. Okay. X equals to constant surface will be having ax direction. Y equals to constant surface will be having ay direction. Z equals to constant surface will be having az direction. Okay. Suppose what is this ds? ds can be written as, okay, ds can be, how the ds can be written as, in the direction of ax plus in the direction of ay plus in the direction of az. Okay. So how can we write? In the direction of ax, suppose if we take x, y and z, suppose if we take the differential volume like this, it is placed on the yz plane. So this is differential volume. This is x equals to 0 plane. X equals to 0 plane. X equals to 1 plane will be like this. X equals to 2 plane will be like this. Okay. Suppose if I want to write this, this is x. X equals 0, x equals 1, x equals to 2, x equals to 3. So how the surface is moving? The surface is moving normal to this. The surface is moving normal to this. Then what is the differential area? The differential area, it is dz, it is dy. What is the area of this? The area of this for x equals to constant surface is, dz into ay. dy into dz. So dy into dz, what is the direction of the surface? Ax. So I can write here Ax dy dz. So in the direction of x, what is the surface area? In the direction of x, what is the surface area? This surface area. What is this surface area? Dz into dy. Like this. In the direction of y, what will be the differential length surface? In the direction of, see, if you observe this is Ax. In the direction of Ax, these are the measurements, okay, dy and dz, okay. So in the direction of Ay, what are the differential lengths? Here dx and dz, right? In the direction of Az, what is this? Dx and dy. So this is the differential volume, differential surface area in the direction of x, differential surface area in the direction of y, it is the differential surface area in the direction of Az. Okay, so because of the time limit, so I am explaining this, so that's why you have to remember this, okay. So otherwise we can represent the graphical representation, but because this is a crash course, so we have to learn the things within the short time, okay. So how can I write in the generalized form? How can I write in the generalized form means ds in the generalized form can be written as, suppose in the direction of AU it will be H2 H3 dV dW AU plus in the direction of AV. In the direction of AV means what? This one. I have to write remaining 2. Remaining 2 is H1 and H3 du and dW. Understand? Now in the direction of AW, I have to write H1 H2 du dV. This is the generalized formula for the differential surface area. Okay, it is the differential surface area in the direction of AU, it is the differential surface area in the direction of AV, it is the differential surface area in the direction of AW. Suppose already, see, for the Cartesian coordinate system, what is H2 and H3? H2 H3 is 1 and dy dz Ax. This one. Okay. In the direction of AY, what is this? 1 into 1, 1 dx dw means dz. Okay. 1 into 1, this is dx dy az. So this is for the Cartesian coordinate. Okay. So now what is the differential surface area in the direction of in the cylindrical coordinate system? In the cylindrical coordinate system, in the direction of A rho, direction of A phi plus in the direction of Az. So what are these values? What are these values? In the direction of A rho, I have to write H2 H3. H2 H3 is what? H2 H3 is 1 into rho into 1. It is rho d phi dz. Rho du dw. dv dw. d phi dz. In the direction of A phi, what? H1 H3. H1 H3 is 1 into 1. 1 into what? du dw. du is d rho dz. Okay. In the direction of Az, what is H1 and H3? H1 and H2. H1 and H2 is 1 into rho du means d rho dv. dv means what? d phi. So this is the differential surface area in the cylindrical coordinate system. Understand? So now, what is the differential surface area in the spherical coordinate system? The spherical coordinate system H2 H3. H2 H3 is r square sin theta dv dw. dv dw means d theta d phi into ar plus. What about this? H1 H3. H1 H3 is r sin theta du dw. du dw is what? dr d phi. It is a theta plus H1 H2. H1 H2 is r. Understand? R du. du means dr. dv means d theta. It is a phi in the direction of a phi. So this is the differential surface area in the direction of in cylindrical coordinate system. Sorry, it is spherical. It is spherical. Now, so what is dv? dv is equal to, this is differential. See, this is the differential surface area in the direction of AR. It is the differential surface area in the direction of A theta. It is the differential surface area in the direction of A phi. So that means what? AR means this differential surface area is used for the R constant surface. Observe clearly. This differential surface area is used for the X constant surface. This differential surface area is used for the Y constant surface, and this differential surface area is used for the Z constant surface. You have to note this. Okay, come to this. What is this? This differential surface area is used for rho is equals to constant surface, and this differential surface area is used for phi is equals to constant surface, and this differential surface area is used for the Z is equals to constant surface. Okay, and this differential surface area is used for the R is equals to constant surface, and this differential surface area is used for the theta is equals to constant surface, and this differential surface area is used for the phi is equals to constant surface. Why I am writing this? See, x equals to constant surface, the surface direction as ax. For y equals to constant surface, the surface area is ay. For z equals to constant surface, the surface area is az. Similar to this, everything I have written. Okay, this is very, very important. And the final thing is the differential volume. What is the differential volume? It is just like LBH. Differential volume. The differential volume, it is represented with dV. dV is equals to what? dV is equals to H1 H2. I am writing this dV because I have used this V here, right? So that's why H1 H2 H3 du dV and dW. So this is the differential volume. Okay, so this is the generalized formula. Suppose if I want to write the differential volume in the Cartesian coordinate system, this dV is equals to H1 H2 H3 1 into dx dy dz. Okay, this is for the Cartesian. Okay, suppose if I want to write the differential volume, what about this? What about this? H1 H2 H3. H1 H2 H3 is rho into 1 into 1 d rho d phi and dz. This is for the cylindrical. Okay, what about dV in the The spherical coordinate system. dV in the spherical coordinate system is what? R square sin theta h1 h2 h3 r square sin theta dr d theta d phi. This is in the spherical coordinate system. Okay, so these are very important, and this table should be in the mind. Okay, no need to go for the graphical method, and no need to bother about the graphical methods also. You can directly follow this, okay, for each and everything, and it will be helpful while calculating the what is that called, the divergence and curl. The divergence and curl can be calculated for the Cartesian coordinate system, but it will be very difficult to find the divergence and curl for the cylindrical and the spherical coordinate system. So there you must use this, otherwise automatically you may go wrong. Okay, so that is the thing, you have to write this scaling parameters and the generalized formulas. Okay, so this is the entire Cartesian coordinate system, and differential length, differential surface, and differential volumes, and the unit vectors. Okay, and all the unit vectors are what? All the unit vectors are orthogonal to each other. Okay, and one more important thing is the ranges of x, y, z. The range of x, y, z are minus infinity to plus infinity, and the range of rho is, what is the range of rho? Here x, y, and z, these are in between what? Minus infinity to plus infinity. Okay, what is rho? Rho is from 0 to infinity. What is phi? Phi is from 0 to 2 pi. You have to note this. And z is, already we know, this is minus infinity to plus infinity. Okay. Now, what is r? R is from 0 to infinity. What is theta? Theta is from 0 to pi. What is phi? The phi is from 0 to 2 pi. So, unless he has not given the ranges, you have to remember these values. Suppose if he has given the range of the r, theta, pi, and rho, phi, z, and x, y, z, you have to use that. Otherwise, you have to use these values. Okay, he will mention either by graphically or by theoretically, he will mention the range of these values. Okay, you have to follow these ranges and the conversions from one coordinate system to another coordinate system. Okay, these are all very important. Okay, so till now we have discussed what? Some basics of the electric fields, magnetic fields, and how the electric fields are generated, how the magnetic fields are generated, how the electromagnetic fields are generated. Okay, what are the causes, different causes of the electric field, what are the different causes of the magnetic fields. Okay, and after that, what is the divergence expression, what is the curl expression. Okay, these are very important. So that's why I have I started with that. So to recollect all these things, I started in the very first hour. Okay, so after that we come into the del operator. A del operator is a vector operator. It is used to what? It is used to analyze the rate of change of quantity in the direction of space. Okay, it can be operated on the vector, scalar, and on itself also. If it is a vector, if it is operated on a vector, it is called as the gradient operation. If it is operated on the vectors, there are two types of operations. One is divergence operation, one is the curl operation. Okay, if it is operated on the del operator, then it is called as the Laplacian operator. Okay, so these are the things. Now the measure of field strength at any point can be determined by using the four vector quantities. What are the four vector quantities? Intensity vector and density vectors. One is E, H, B, D. Okay, these are very important. Okay, and also the measure of field strength is also dependent on the medium, that is epsilon and mu. Okay, so like this. So what the Gauss law is saying? The Gauss law is saying that the net electric flux leaving any enclosing surface is equal to the charge enclosed in the volume. Okay. Now what is the Ampere's law saying? The total circulation of the magnetic field on any closed line is equal to the current crossing the surface. Okay, that is Ampere's law. Okay, so that is Ampere's law and the Gauss law. And what the Maxwell has did, the Maxwell has collected all the equations from the Gauss law and the Ampere's law, and he has given his own explanation. Okay, and also he developed two more equations, that is closed integral E dot dl is equals to 0 and closed surface integral V dot ds equals to 0. Okay, and he proved that the electric flux lines are, he said that the electric flux lines are the conservative in nature. That means they never cross, they never form